minutes.
Okay, thank you, Loic, and hello everyone. So yeah, in my title I'm saying homotopy type theory, but in this talk I will mostly be focusing about normal identity proofs in ROC or in normal map-and-left type theory. The only thing is I'm not requiring any uniqueness of identity proof or axiom K or anything, just vanilla. All right, so first I'll recall how we or how one would deal with identity types in ROC in general. So let me start with an example. If you have a proof P that X is equal to Y and a proof Q that Y is equal to Z, then you may know that you can prove that X is equal to Z. That's what usually is called the transitivity of identity of equality, let's say. And well, this is a fairly easy proof that you can do in ROC. You just, well, first obviously you introduce everything and then you do induction on Q and then induction on P, and then you're left with just something that can be proved using the reflexivity tactic. Okay, so let me explain what's going on under the hood a little bit. So under the hood, this equal sign, which defines identity in ROC, is defined as an inductive type, and it has only one inductive constructor, which is called EQ-REFL, which is the reflexivity that assumes that both terms x, like both terms on the either side of the equality are definitionally the same. And this is what we're doing here. We're inducting on that inductive type. So actually, I didn't need to write it as like using tactics and proof. I can write directly a proof term that does exactly the same thing. What I'm going to do is I'll match onto Q, which is an equality. And in the unique constructor case, which is EQ-REFL, I will match onto P. And in the unique constructor case, which is EQ-REFL, I just have to give an equality that now I'm reduced to giving an equality between something and itself, and that's just going to be EQ-REFL. So as you can see, this proof is a bit seems a bit silly. It doesn't seem much that it has much information in it, but this is something that we certainly need to do. Also, I should say this is not the only way you could prove transitivity, but this is the one I want to focus on for now. Okay, so let me now give you a more involved example, slightly more involved, which is something that we call whiskering in category theory, but you don't need to know about that to understand what's going on. So just imagine now that you have a proof P that X is equal to Y and another proof Q that X is equal to Y, together with a proof A that P is actually equal to Q. And then you have a proof R that Y is equal to Z. Then you can prove that the transitivity of P with R is actually equal to the transitivity of Q with R. Okay, that sounds again a bit silly. And how would you prove that? Well, you do something that looks very much like what we did before. So first you introduce all of your variables and then you pattern match onto R. You have only one case, which is reflexivity, a EQ-REFL. So in that case, you pattern match onto A, which is EQ-REFL, and then you pattern match onto P, which is EQ-REFL. Note that because I already pattern matched A onto EQ-REFL, I don't have P and Q anymore. I just have a single P, right? And at the end, I just have to give a proof of an equality, but it turns out that this equality is just an equality between two things that are definitionally the same. So I can just give EQ-REFL as a proof. Okay, so those two proofs are purely structural on identity. Like, I'm not talking about transport. I'm not talking about interaction between identity and other structures. This is just about identity and identity over identities and identities interacting with themselves. Okay, you can also notice that the proof strategies are extremely similar. Just pattern match everything against EQ-REFL, and at the end, I just have to give a proof, and that proof is going to be EQ-REFL. Yet, even though they seem a bit silly at first, there are actually non-trivial examples of things you can do with that, and this is a non-trivial structure. And for that, I will show you the Ekman-Hilton example at the end of the talk, but for now, just please trust me, this is not a very, like, you can produce non-trivial structure out of that. And so the aim of this talk is to try and streamline these arguments as much as possible, as much as we can, so that we don't have to do some sort of complex guessing proof or writing a proof term manually by pattern matching everything onto reflexivity. Okay, so in order to do that, I'll introduce a notion that's called weak omega groupoids and a language for them, which is called CAT. And I'll explain to you how they are related to identity types. So first, weak omega groupoids, they are like an algebraic structure, something that people study in mathematics. And they describe exactly the structure of those identity types. So they encompass exactly the sort of arguments that we want to streamline. It's just purely about identities, no interaction with anything else. If you know about category theory or higher dimensional categories, there are some sort of flavor of that, but I'm not assuming any prior knowledge of categories for this talk. In this talk, I will not present weak omega groupoids formally because it's a bit of a mouthful, but I want to introduce a language which is called CAT, which is a DSL in order to work with what's called weak omega categories. So you might notice that I said weak omega groupoids and then weak omega categories. Well, weak omega groupoids are a special case, and for reasons that I don't want to delve into in this talk, CAT is a language for weak omega categories, not weak omega groupoids. So that means that we can do everything we can do in CAT, we can interpret later on as construction on identity types, but we might miss a few things. But for the purpose of this talk, I will ignore that completely. So for you, just think about CAT as a language for maybe abstract identities. It doesn't do everything, but that's fine. Okay, so in order to introduce CAT, I need to introduce a notion which is called a pacing diagram. And intuitively, those pacing diagrams are going to be a class of diagrams or equality schemes that we can pattern match away completely against this reflexivity. So I want to draw your attention that it's not going to be all possible diagrams that we can pattern match away, but it's a large class of them, large enough. And let me give you a few examples. So the first example is the one that corresponds to the transitivity that I showed before. And I'll introduce a syntax in order to talk about this. You can see that we have X, Y, and Z, which are points in this diagram. And so I'll represent them as variables names in the first layer of parentheses. And then you have P, which is an equality between X and Y. And in order to represent that, I'll add parentheses and P between parentheses. And now I'll understand P as an equality between what's on the left of the parentheses and what's on the right of the parentheses. So P is an equality between X and Y in this example. And Q is an equality between Y and Z because on the left of the parentheses for Q, you have Y, and on the right, you have Z. Another example is the one for the whiskering that, again, I introduced before. And I'm using the same syntax, same sort of principle, but now I have an equality between equalities. So I have a second layer of parentheses in which I have A, and you can see that A on the left of the parentheses, you have P, on the right, you have Q. So A is a parenthesis, is an equality between P and Q, sorry. And if you look at P again, on the left of the parenthesis that contains P, you have X, and on the right of the parenthesis that contains P, you go like all the way to Y, and so P is indeed an equality between X and Y. And this syntax that I'm introducing now, it will enforce that the sort of like it describes an equality scheme, like a bunch of points and equalities between them, but in a way that enforces that it can be pattern matched away against reflexivity or a QREFL. This comes from literature about higher categories that you don't need to necessarily understand, but just a few pointers. This ties in really well with work on Batanin and Grothendieck and Matsimotis. Okay, so in order to understand or get a feel of what pacing diagrams are, we can also consider things that are not pacing diagrams. and we'll understand a bit better what they like, why they are not pacing diagrams, and mostly the obstructions are topological. So the first example is a point X and an equality between X and X. And you may know that saying that, oh, I can pattern match against this shape is the same as axiom K, is exactly what axiom K says. But vanilla Martin-Love type theory doesn't have axiom K. It has a different axiom for identity, which is called J. And so I'm not requiring that this is a pacing diagram, and I actually don't want to require that, because I don't want to introduce axiom K. I want something that works in vanilla Martin-Love type theory. Similarly, if I have X and Y, which are 2 points, and P and Q, which are 2 equalities between X and Y, but I don't require those 2 equalities to be equal between each other, that's also not a pacing diagram. That's also an obstruction. Why? Because I can pattern match Q onto EQ raffle, and that will identify definitionally X and Y, but then P becomes a loop, an equality between X, and I'm back to the previous case where I would need axiom K, and I don't want it. Okay, so hopefully you have a sort of a feel for pacing diagrams, how to express them and what they are now. And so let me introduce the language cat. Again, I'm like simplifying stuff because I don't want to deal with groupoids versus categories, but ignoring that, cat is a language where I have 2 sorts of type. I have type that I denote star, which is kind of like a base type, an arbitrary base type if you want. And then I have A tilde B, where A and B are both terms of the same type. So the intuition is that this A tilde B are abstract equalities. They are not equalities in Roc, they are equalities in cat. So they don't compute as in Roc, but they're purely abstract schemes of equality. Okay, and the terms are going to be, well, either variables. Of course, a variable is a term as it's usual in type theory, but also terms of the form gamma A with gamma pacing diagram and A type in gamma. So what's the intuition behind that? Well, remember that the intuition behind pacing diagrams is that we can construct everything away onto reflexivity. So if I have a type in a pacing diagram, by iterating this pattern matching onto this pacing diagram to get back to a single point, I can inhabit that type by providing the proof, which is just the reflexivity proof. And this thing is meant to represent that construction, that filler. So what I'm saying here is in every pacing diagram, everything that I can construct, there will be an inhabitant. And yeah. Note that in the implemented language, again, we have additional conditions on type A because of the difference between groupoids and categories. Okay, let me give a very, very small demo of cat and how it works. So here, hopefully you can see on my screen, I have this co-transitivity and then a bunch of arguments. These arguments, you may recognize here something like the syntax for pacing diagrams, and the diagram that this describes, again, it's P, which is an equality from X to Y, and Q, which is an equality from Y to Z. And then I give a return type. So I want to say this is a coherence. Here is the type that it will inhabit. And here it will inhabit the type X to Z. So in the actual implementation, I'm using arrows because of categories again. But I chose to write it with a squiggle because in the slides, because I want to consider them in this case more like abstract equalities. Okay, so now, so this is the proof of transitivity from X to Y to Z. I can go directly from X to Z, and then have the proof of the whiskering, which is transitivity of P and R is equal to transitivity of Q and R, where I have this pacing diagram here, which again, hopefully you recognize it is this one here, the second one that I have drawn. All right, so now that I have introduced cat and we can make groupoids, how does that help us to write identity proofs? Well, the idea is I have a plugin in Roc that uses terms in cat in order to generate proofs on identity terms in Roc. So first, there is a lot of boilerplate inductive mechanism because all the theories are defined by induction, and you have to manage all of this induction away. That's not very hard, and that's not very interesting. That's not where the structure is. The structure is on the base case. The base case is that of a term of the form co of gamma A, where again gamma is a pacing scheme and A is a type. And what we're going to do is we're going to remember that pacing schemes are meant to represent equality schemes that we can pattern match away completely onto a single point. And we're going to just do that proof by pattern matching. And at the end, we have to give a proof for A, but after pattern matching, the proof for A is always going to be eq-referral. It's always going to be a proof that something is equal to itself. Okay. I also want to note that in that plugin, the implicit arguments are managed completely automatically, so you don't have to deal with which arguments are explicit, so that I will show you the plugin right now, and that's just so you're not disturbed by that. Okay, so yeah, let me show you the plugin now. So if I go on my Roc file, first I have this plugin that I can load. And then this plugin gives me access to this command, which is the cat command, to which I need to give a list of names and then a file in which to get those names. So the file that I'm giving here is the file I just showed you before, where there was like trans and whisk. And here I'm saying to the plugin, please look at the terms trans and whisk and extract the corresponding Roc proof on equalities from those. Okay, let's do that. And so it tells me, oh yeah, it's done successfully, sorry. Sure. And if I now print this term, so yeah, I've been made aware that I didn't have to give names to every variable, but for now the names are generated automatically. So if I print this term, you can see that the names are, first you can see that the names are a bit horrible. But if you abstract the names away and try and think with better names, you can see that it does pattern matching on one argument. When this argument is reflexivity, it does pattern matching on the next one. And when this one is eq-referral, it gives eq-referral as a proof. So it does exactly what I set out to do, which is streamline this sort of arguments where I pattern match successively onto reflexivity. Let's look at the whiskering just for good measure, but it does exactly the same. So if I look at the whiskering here, let me isolate. So this is first the context, but let me isolate the part of the proof that's interesting for us, which is pattern match something with eq-referral. In that case, pattern match something with eq-referral. And in that case, pattern match with eq-referral and give eq-referral at the end. So this is really like the proof of the whiskering that I gave at the very beginning. You can see that the pattern match are a bit like wordier or more verbose than the beginning because I'm giving return clauses and giving everything, but that's because I'm talking to the Roc kernel, so I have to give everything to the Roc kernel. That probably is a better way to print this, by the way. This is a bit experimental at this point. Okay, let me come back to my slides. And now, what have we gained now? Because I've told you like, oh yeah, we can spare ourselves from doing the Roc proof, but instead I have to give a cat proof. And well, maybe it's a bit easier to give cat proofs, or at least it's a bit less verbose. It's a bit shorter, but yeah, it's not that much simpler. So the thing is, with cat, we have a very simple language with a very, very direct focus. Its only purpose is to deal with these problems of, let's say, coherence or identities in every places. And Roc is a very general purpose language. It's very wide, it's very good, but it's very complicated. So going into cat, we can now manipulate the cat terms a lot more easily. And indeed, we have implemented several meta operations. So this is something I've done a long project of mine implementing meta operations in CAT. And so, for instance, I have suspensions, opposites, and something called functoriality, naturality. I don't want you to understand what they are necessarily, but these come from higher category theory. And this, from these considerations, they let me write good meta operations or write CAT proofs in a much simpler way. And since we can export CAT into Roc, now we can also leverage those meta operations or the structure, the very structure of identity types and the higher category theory that is baked into CAT in order to build our identity proofs in Roc. So this is what we gain in the end. So I promised you to talk about the Ekman-Hilton argument very quickly. So the Ekman-Hilton argument is a very important argument in topology, and this is my connection in this work to homotopy type theory. So the people who care about Ekman-Hilton argument are mostly homotopy theorists, and in Roc they would try and prove such thing using homotopy type theory or using the hot plugging of Roc. But it's proven purely by structural manipulations on identity types. It really doesn't require any univalent axiom. It doesn't require any higher identity types, any of that. It's just purely the kind of arguments that we set out to streamline in the beginning. And it's also important for, I mean, this is not very relevant for the talk. It's just for, as a side note, Ekman-Hilton argument is also important in the field because it provides a refutation of axiom K in some model. So it shows that K is not derivable in plane Martinov type theory. Okay, so let me give you a very small example of what the Ekman-Hilton argument looks like. So this is in my demo2.cat file. I'm not at all expecting you to understand what's going on here. However, what I want to point out is that at some point you can see suddenly I have square brackets here. I have underscore here. Well, underscores are quite easy because they're just implicit argument, but square brackets are one of those meta operations that I was talking about. So when I encounter something with a square bracket here, I'm just writing a term in a much shorter way, but it will generate a much bigger term when it's looked at. I have this up here as well, which is also one of those meta operations, and so on. So this construction here, you can see it's 22 lines at the end. It's not that big, but it makes heavy use of a bunch of meta operations. And if I run cat onto this, it will print a somewhat longer term. I'm aware the output is not very readable, but the point is just to show you it prints a somewhat longer term because actually all of these meta operations get expanded into real operations. So real either variables or co, which are the things that are there in cat, right? Okay, so again, 22 lines of input. And now I go into my Roc demo file. If I tell, oh, can you please get cat into Roc, Ekman-Hilton into Roc using cat, that works. And I can print the file. So here it's not very readable, but you can see that it generates a really big, complicated term that you wouldn't really want to generate by hand. And if I evaluate the file completely, firstly, you can see that it is very, very big. It gets very, very big. But secondly, you can see in the structure, it's just a bunch of pattern matching of a bunch of things that are pattern matched away, a bunch of things that are pattern matched. And everything is pattern matched onto eqrefl. And at the end, we just provide eqrefl. So this is just an argument of the nature of things that we had seen before. It's just a much more complex one. And by complex, I mean mostly combinatorially complex. It has a lot of branches, but by providing a small, let's say, a small skeleton of it in cat, I could just generate that entire thing in Roc directly. Okay, so that's it for me. Thank you.